that. We will come back to it when we are ready to talk about corrections to the Gaussian model, which, before getting into that, want to get into the discrete models which we started with, but left at some point. So back to the Ising model, which we used as the prototype for mean field theory, and obtained answers which are, well, I mean, gave you beta equal to half, gamma equal to 1, and so on. Delta was 3, and you cannot get nu or eta or alpha or even alpha. I mean, in the sense that alpha is trivial, the mean field magnetization just has a finite jump. So whether you whatever you may call that as a picture of alpha, but certainly there is no exponent alpha in the mean field theory. So nu and alpha are absent, and you have certain values for this. So we now want to pick up a different, go back to the Ising model and see whether we can get a better picture of things by going to the Ising model and trying to do the calculation in somewhat different framework. Before the different framework, one has to go dimension by dimension. D equal to 1, the standard easily solvable or easily exactly solvable model is always the starting point. The D equal to 1 is familiar to most of you, but there could be some who are, and also it is good to for taking the next step, which I will also through the D equal to 1. So I want to start with the D equal to 1 Ising model, nearest neighbor interaction. So nearest neighbor interaction, and these are spins, Ising spins, which can point only up or down. So just two available states. So it's a chain of this kind. What is the Hamiltonian or the interaction energy, the energy of the system? Energy of the system is summed over nearest neighbors, and J I J S I S J. So it is summed over nearest neighbors, which means the Jij we will take independent of site, and so this is equal to summation J S I S I plus 1. So I equal to 1 to n, and it is going to be attractive interaction, that is the energy, if the spins are parallel to each other, the energy is lower. So I will put a minus J over here. This one-dimensional model over here cannot have a phase transition. The argument is that I want to look at what is the equilibrium state. The equilibrium state is the minimum of the thermodynamic free energy. So equilibrium state is the minimum of the thermodynamic free energy. The thermodynamic free energy is F equal to internal energy minus T times S. So let's imagine the 1D Ising has an ordered state. So I have an ordered state, and which means that, let's say, all spins are aligned. I want to, so this has to be a state of minimum free energy. So any disturbance that I do to this state has to raise the free energy of the system. So this is my ordered. I assume that at any temperature T, at a T not equal to 0, there is an ordered state, and I want to see whether this state is stable against perturbation or not. That is, I will increase the energy of this state slightly and see whether that causes the free energy to increase or not. If it does, very good. I have the ordered state is perfectly all right. So what is the excitation which is the minimum energy? It is what do you think is the answer? What is the minimum? So what I'm looking for, the minimum energy excitation. So what does the minimum energy excitation look like? What will be the configuration? The question is that I want to disturb this ordered state in such a manner that the excitation energy is the lowest possible. The energy is this chap over here, mind you. So that is the energy, and I want to disturb this ordered state so the energy cost is minimum. So what is the minimum energy cost? This is a configuration. I want to see what is the configuration. So over here the energy is minus n times j. what is the energy of what is the next higher energy? What is the configuration which will give me the next higher energy?
That minus nj plus 2j.
What is the configuration? A second. For the state that you are saying, what is the configuration?
Sir, any two neighboring spins are opposite, and all on the right, let us say the spins are one direction in one direction, and the left of that particular spin all are in the down direction.
Audio. Are you saying that? Are you saying that it is? Huh?
Yes, sir. Yes, sir.
Yeah. Okay. That is the configuration, which is the minimum excitation, which costs only one spin flip. So what was the energy minus J has now become plus J. So delta E, if I make that change, then delta E is equal to 2J. All right. So that is a contribution from here. What is delta S? So N so what is the entropy? No, it's much simpler because S is equal to K log gamma. Gamma is the number of possible configurations. So how many configurations? I can put this break anywhere along the chain. So there are n configurations. So delta S is equal to K log n. So delta F is equal to delta E minus T delta S, which is equal to minus Nj plus, sorry, minus, what is this Nj? 2J. Which is equal to 2J minus T K log N. So 2J minus KT log N for all T not equal to 0, I can always choose a N which is larger than 2J. So in the thermodynamic limit, the just flipping, going to the next or higher energy state lowers the free energy, and hence the ordered state is unstable. Consequently, the one-dimensional Ising model cannot have a transition to an ordered state at any finite temperature. So the transition temperature has to be T equal to 0. So, all right, so assignment in this stage is that suppose suppose I introduce the Gij so it's Jij Sisj E is equal to summation over the all the relevant I and j's, and if I am now going, what we had was that regardless of I and j, for all pairs of spins I and j, Jij was a constant, and we restricted j to I plus 1. I'm now saying that Sj can be anywhere, Gij is non-zero, except that it is equal to 1 over I minus j mod raised to the power, let's say, alpha. So Jij is falling off interaction. If the spins are far away, then it is certainly going to tail off to 0. And so alpha is positive. The situation which we dealt with was that it is absolutely short range, meaning that Ij had to be nearest neighbor in order that. So I'm changing the nearest neighbor to falling away interaction high when the particles are close, and so alpha is greater than 0, Gij is I minus j. Find the critical alpha c below which there is a finite temperature ordered state. The argument has to do with what we did a few minutes ago, that you have to change the config, ask for whether the free energy has increased or decreased. So it has to be, it has to do with the argument that I just gave, except that now the nearest neighbor has been replaced by the neighbors are, if the neighbors are close, the interaction is strong and it decays. And the point is that if the interaction is strong enough, in these infinite range interactions, if the interaction is strong enough, there is going to be a phase transition. There is going to be an ordered state, but if that for strong enough, meaning the alpha has to be small enough so that it has a long range component, significant long range component. I mean, if alpha is like 10 or 12, that's as good as saying that there is no long range part over here. And so long range forces from, we are making the argument that I showed you was for the nearest neighbor, the most short range force imaginable. And now the point is, if that kind of argument, what would the answer be if it is a long range force? Very good. So, all right. So that's the if I solve this Ising model, I don't expect to get any phase transition except at t equal to 0. So, all right, but let's make sure that that is what I get. And when it orders at t equal to 0, what kind of a behavior does the susceptibility or correlation length, etc., have? So that is the question that we want to answer. So here is the nearest neighbor Ising model along a line, and I need to evaluate the partition function, which is z equal to, and in an external field, so that there is a external field and this. So you add on an external field so that you can control the susceptibility, etc., and so on. So partition function has to be evaluated, which is z equal to beta summation I equal to 1 to n beta j over here si plus 1 e to the power beta h, and it is summation si. What we will do, we will introduce what is called a transfer matrix, which most of you are familiar with from a previous course. I'm sure that so, but not all of you, and we need to get the transfer matrix done. So there is this transfer matrix. The philosophy is, imagine problem solved up to the nth site. And question is, what do I need to do to solve it with n plus 1 sites? That is the question. So you imagine that it is solved with n sites, and then I need to know what do I do if. So the so you start by noting that this partition function, let's suppose the nth spin is up. So I hold the nth spin up and calculate the partition function, which I call Zn plus. And then I do the same, and with the nth spin down, I calculate the partition function and call it Zn minus. Now I imagine that I add another spin, and we now have Z n plus 1 plus and Z n plus 1 minus. What I want to do, the transfer, the matrix is what will take you from this stage over here to this stage over here. That is what this transfer matrix is all about. That the problem till the nth step taken to the n plus 1th step. It's a relation between n plus 1 term partition function and the n term partition function. So how do I relate them? I relate them by, let's look at Zn plus, so here is my nth spin. Let's say, so this is n and here is my n plus 1. So n plus 1, Z, if it is up, then the relevant thing is Zn plus 1. So Zn plus 1 can come from this as well as this. So the nth spin could have been up, in which case the contribution to Zn plus 1 will be from this, and the nth spin could have been down, in which case the contribution is going to be from this. So Zn plus 1, if up, so I'm looking at this one, Zn plus 1 up is Zn up, which is this, and then I have to add the relevant part of this. The relevant part of that is Sn plus 1. So Sn and Sn, and both of them are positive. So it is plus 1 for both, and I get e to the power beta j. Now I come to this term over here. It is n and n plus 1, both are up, and therefore I have 2 times beta h. Okay. Now if I plus, it's Zn minus, which is this one over here. So then it is Zn minus, and now the beta j, one of them is up and the other is down. So it is e to the power minus beta j, and over here it is 1 plus minus 1, which is 0. So this is Zn plus 1, which is Zn plus this into Z. And Zn plus 1 minus is going to be, if this is this is what. So Zn plus 1 minus, when I'm talking about this one over here, which is with Zn plus, then it has to be the e to the power minus beta j, and that's that. And when it is Zn minus, then it is e to the power beta j, and then it is minus 2 beta h, right? So e to the power minus beta j minus 2 beta H, plus beta J minus 2 beta H. So this column vector, if I think of this as a column vector, this is equal to a 2 by 2 matrix, which is my transfer matrix, times Zn plus this column vector. So this is the philosophy of the transfer matrix, that I have gone from the nth site to the n plus 1th site by this matrix over here. The matrix now written down explicitly is matrix T is equal to e to the power beta j, e to the power beta j plus 2h, e to the power minus beta j, e to the power minus beta j, e to the power beta j minus 2h. So that's the transfer matrix, and it takes me from one site to the other. So now you can do what? You go from this to the next to that and down to a situation where you just have one spin, which can be up or down. Huh? So I mean, that is one, the lowest, which is 2 spins, maybe. So what you have is that Zn plus 1 is at the last point, you have some will go. So this matrix will go T times something equal to T square times the previous, and after n steps will be T to the power n, and then some alpha beta, which is the lowest order vector. All right. So the transfer matrix is for this T, and you calculate this quantity Zn plus 1. So this is this vector at this stage. So at this stage, you calculate the Zn plus by starting with some unknown initial condition alpha beta, and then you go on applying this matrix several times, and eventually the Zn plus 1 is equal to this T to the power n is T to the power n alpha beta, and the Z is simply Zn plus 1 plus Zn. Okay. So that's the partition function. So all right, so what? How are you going to, so now why is that a great simplification? It's a simplification because all that I need to do is now write down the eigen. If I have the look at the T and get its eigenvalues, the transfer matrix eigenvalues lambda 1, lambda 2, eigenvectors which are whatever corresponding to that, let's say alpha 1, alpha 2, beta 1, beta 2. So if I know the alpha eigen, then I can simply write down that this at the end of the day, Zn plus 1 is your lambda 1 to the power n alpha 1 alpha 2 plus lambda 2 to the power n beta 1, beta 2. So that has to be the final structure of this Zn plus 1, Zn plus this Z matrix. So your partition, which is the Zn plus 1, looks like this, and the partition function is going to look. Shouldn't have erased that. And Z is that. So that's the story. That's the end of the thing. So all right. So now what? So all that is required of me is to write the eigenvalues of the find the eigenvalues of the partition of the transfer matrix. So once I have the eigenvalues of the transfer matrix, I'm through. So the transfer matrix was e to the power beta j plus 2h, e to the power minus beta j, e to the power minus beta j, e to the power j minus. That was the transfer matrix, and the eigenvalues so the eigenvalues would be given by e to the power beta j plus 2h minus lambda into e to the power beta j minus 2h minus lambda, that is equal to e to the power minus 2 beta j. So e to the power 2 beta j minus lambda e to the power 2 beta h minus e to the power minus 2 beta h e to the power beta j plus lambda square is equal to e to the power minus 2 beta j. That one needed was a blackboard instead of a whiteboard over there. So, so it is lambda square minus 2 lambda sine hyperbolic 2 beta h plus 2 cos hyperbolic beta j equal to 0. Lambda is equal to sine hyperbolic 2 beta h plus minus square root it is now have this is going to be in principle I should have a 2 over here, but there is a 2 in the bottom, so that's why I cancelled. But now I have to write b square, which is 4, so it is 4 sine hyperbolic square 4 sine hyperbolic square 2 beta h, and then it is your minus 4, and it is cos hyperbolic it's not, sounds a little off. Lambda, it should have been a minus here, right? It's lambda square. That's a minus. It's e to the power 2 beta j minus e to the power. So it is a sine hyperbolic, right? It should have. It is a sine hyperbolic 2 beta j beta. So it is sine hyperbolic square 2 beta h minus 4 sine hyperbolic 2 beta j. The 4's go out, and that is that. So sine hyperbolic, because there is a 2 in the bottom, so it is sine hyperbolic 2 beta h plus minus. Looks a bit. Something seems missing. Something seems missing. What is missing? This is what is missing. So here is, it is sine hyperbolic e to the power beta j. This is 2 sine hyperbolic beta h e to the power beta j. And over here, there is e to the power 2 beta j. That's it. Now things look better. Okay. So lambda is equal to this. So there is a plus and a minus. So one root is greater than the other, which means that if I now look at this over here, n is large. So the large in the thermodynamic limit, when n goes to infinity, limit n going to infinity, larger lambda survives. So the larger lambda is the one with the positive sign, and therefore you have the result that the this is, sorry, Likani, lambda square minus 2 lambda sine hyperbolic 2 beta h e to the power beta j plus cos 2 cos hyperbolic beta j is equal to 0. So sine. Sir, thank you. Yes. So it is e to the power 2 beta j sine hyperbolic square 2 beta h, right? So that with a 4. Yeah. Right. The 4 into 2, is that what you're talking? 4 into 2, right? Thank you. Yeah. This would be vital later. All right. So so Zn plus 1 I mean, this reduce, so z, which is plus, is lambda 1. So essentially, this is lambda 1 to the power n alpha 1, and therefore z n is plus 1 is equal to lambda 1 to the power n and alpha 1 plus n. The free energy, so that is the large n limit. That is the partition function, and therefore the free energy is F equal to minus kT log Z is minus n kT log lambda 1 with plus constants. So to within additive constants, it is just n times nkt log lambda 1. Log lambda, which for lambda 1? Now lambda 1 which is bigger, lambda 1 is the one which is bigger. Therefore, lambda 1 is e to the power beta j sine hyperbolic 2 beta h plus square root of this quantity over here. Now, so the time of reckoning, because whether one gets, so the up to this, it was just some maths. Now comes the physics, because the magnetization needs to be calculated. The magnetization is minus del F del H. So that at constant T, and therefore I need to calculate. So this is equal to n kt lambda 1, and then it is d lambda 1 dh. So this is, so I need to calculate d lambda 1 dh. So this is my job. So d lambda 1 dh is e to the power beta j 2 beta cos hyperbolic 2 beta h plus half. And then this square root business over here. And now I have to take a derivative with respect of this quantity with respect to h, right? So it is e to the power 2 beta j, and then it is 2 sine hyperbolic 2 beta h cos hyperbolic 2 beta h into 2 beta, right? Into 2 beta. Huh? This is equal to, this is del lambda. Huh? So what factors out? The 2 cancels this 2 here, right? And the 2 beta factors out. Is that correct? 2 beta factors out e to the power beta j. So 1 e to the power beta j factors out, right? 2 beta factors out, 1 e to the power, we are almost there. If I don't make an error, where the algebra will be over soon. So 2 beta, this is now cos hyperbolic 2 beta h plus. And now there is a cos hyperbolic 2 beta h, there is a sine hyperbolic 2 beta h, 1 e to the power beta j, and then there is this square root over here, right? So this is 2 beta e to the power beta j, and I can factor out a cos hyperbolic 2 beta h, correct? So 2 beta e to the, and then I'm bringing out this, and then it is 1 plus. I have removed this, so 1 plus, it is sine hyperbolic 2 beta h divided by the square root over here, correct? কোথায় ছিল? Oh, second term. Yes, right. Yeah, very good. Beta j. Good. Got it. Thanks. Now look, I take the square root up over here. And what do I have in the numerator? I have lambda 1. Huh? So this I can write as 2 beta e to the power beta j cos hyperbolic 2 beta h lambda 1 divided by the square root over here, which is that mess, right? E to the sine hyperbolic square 2 beta h minus 2 sine hyperbolic 2 beta j, right? There was a e to the power 2 beta j. Yes. Vital. So here is my free energy. What was this that I calculated? D lambda 1 dh, right? So d lambda, so this is equal to d lambda 1 dh. And then you look at, so m is equal to, it is nkt times this. So it is nkt, and then it is 1 over the into this. So it is 2 beta e to the power beta j cos hyperbolic something's gone wrong. Something's gone wrong. M is this, lambda was that. Lambda was so del f log lambda 1 d lambda 1 h, so d lambda 1, so I'm doing something's gone wrong. What has gone wrong? It's the lambda which is wrong. This is okay. Sine hyperbolic has to be the factor here. This is sine hyperbolic 2 beta j, and there is e to the power, so see the answer, the lambda should have a 0h limit, which is what it doesn't seem to have, obviously doesn't have over there. So the zero field limit of this eigenvalue. So the matrix was e to the power, something's gone wrong. This is the problem with these things. The matrix was e to the power beta j, e to the power j plus 2h, or no, it's over here. E to the power j minus 2h or plus 2h, e to the power minus beta j, e to the power minus beta j, e to the power e to the power beta j minus 2h. That was the transfer matrix. That was the transfer matrix which, if h is equal to 0, is the কোথায় বলো তো? Thank you. So e to the power 2 beta j minus lambda, and then it is this plus this. So this becomes a cos. So now this is cos. Sorry, thank you. So this becomes a cos hyper. Everything else is unchanged. Eta. Lambda square minus, this is cos hyperbolic beta h. Cos hyperbolic 2 beta h, and then it is minus 2 cos hyperbolic minus sine hyperbolic 2 beta j. So it is lambda square minus lambda this, and this is plus, right? Lambda square, and this is plus over here. Lambda square minus 2 lambda cos, right? There has to be a e to the power beta j sitting here. So e to the power, so it is lambda square minus 2 lambda cos hyperbolic 2 beta h times e to the power beta j and plus 2 sine hyperbolic beta j. So it is e to the power beta j cos hyperbolic 2 beta h plus minus e to the power 2 beta j cos hyperbolic square 2 beta h, and then that had a 4, and then this has a 4 under 2 8, and it is minus, and it is sine hyperbolic 2 beta j. Okay, so if I take h going to 0 limit, h going still not still correct, h going to 0, this becomes 1. It is e to the power 2 beta j minus this is e to the power 2 beta j minus e to the power so it becomes so it is square root of e to the power minus 2 beta j, so it is plus minus this, and so the yeah, thank you, yeah. All right, so it should have been e to the power this magnetization. So all right, let me get, I think what is wrong here, the square, it should be did I have to change the this term didn't need to be changed, right? Cos hyperbolic to that is what changed. This was a sine hyperbolic which became Wow. Do I need to better? No. No. Right. Will take a couple of minutes, but we need to get it right. So, it is m is d lambda 1 dh. So we are going with the plus sign. That's the higher one. And so I'm doing d lambda 1 dh. D lambda 1 dh is e to the power beta j 2 beta sine hyperbolic 2 beta h plus half and 1 over square root of this. Then on the top, it is e to the power 2 beta j, and then it is 2 times cos hyperbolic beta h. This is derivative with respect to h over here. So it is 2 cos hyperbolic 2 beta h sine hyperbolic 2 beta h and another 2 beta coming from this, and then it is no derivative coming from here, right? So this is this, which is equal to, so now this is going to be, you cancel the 2's, this 2 and this 2, a 2 beta comes out, and you have a lambda 1 on the top, and I have a square root on the bottom, and there is a sine hyperbolic 2 beta h, right? So this is, so d lambda 1 by lambda, so this is equal to nkt, and then it is this d lambda 1 by lambda 1 is 2 beta, then there is the sine hyperbolic 2 beta h divided by the square root of e to the power 2 beta j cos hyperbolic square 2 beta h minus 2 sine hyperbolic 2 beta j. Good. So m is equal to minus del f del h is this quantity over here. The beta cancels out this. So this is out, and you just have 2n. So beta n 1 over kt cancels out. And now you notice that if h goes to 0, right hand side goes to 0 at all temperatures, and therefore there is no zero field magnetization. So no spontaneous magnetization in the system at any finite temperature. If I take h, so this expression, the magnetization for h tending to 0. So for h tending to 0, the magnetization is 2n, and then there is 2 beta h, that is the sine hyperbolic, and now there is e to the power 2 beta j over here and minus this over here, which means that there is e to the power minus 2 beta j, which means that this is e to the power 2 beta j. Correct, right? Is or just beta j. It should be square root of 2 beta j, and this shouldn't be there, right? So it is e to the power minus 2 beta j after the cancellation, and then square root e to the power beta j, and so m is equal to this, which means the susceptibility is the zero field susceptibility is 4n beta e to the power beta j. So the susceptibility is 4n beta e to the power beta j. And now you notice that at t equal to 0, the susceptibility diverges exponentially. So the exponential divergence of the susceptibility at t equal to 0. So these are the characteristics of the Ising model. The free energy is given by this. So one-dimensional Ising model, that's the free energy. The magnetization, the zero field magnetization is not there. The susceptibility at zero field is going to blow up at t equal to 0, which is the transition temperature for the system, as it is for all systems. So t equal to 0, you automatically have an ordered state. So chi diverges at t equal to 0, and the way it diverges is exponential, not the power law divergences that we have been talking about. So the one-dimensional, the specific heat can be obtained by taking two derivatives of this free energy over here, and the specific heat, if you calculate it, would look something like this. So there is a peak at a finite temperature. So all right, so we know the thermodynamic properties. What's the next thing we need to know? We need to know the correlation length. So obviously, as t tends to 0, the system is ordering trivially, but ordering all right. The susceptibility is blowing up as t goes to 0, blowing up very strongly, exponentially, e to the power 1 over t. Question is, how obviously then as t tends to 0, the system gets correlated, and the question is, how do I calculate the correlation function? So what is the correlation function? Which is the expectation value of S1 with, let's say, Sn. So the first spin and the nth spin, or n plus 1th spin, if you want n distances, it is that correlation which you need to find out. So that's the last thing which one wants to calculate with this, that because once again here there is a interesting issue, and I mean that's the issue that we will take over to do something. So I need to get this done. So the system, I need to calculate the correlation function between S1 and Sn. So here is S1, and here is my Sn. That's the chain over here. The correlation function is entirely independent of what is outside to the left over here or to the right. So it is a question of finding out, what the S1, Sn, this weight factor. I have to calculate this weight factor. That is S1, Sn weighted by this e to the power 2 beta j, and the question of divided out by the partition function which we just calculated. Yeah. No. It's nearest neighbor. Nearest neighbor. Huh? No. It's not. I'm just calculating. It's infinite number of. There are. This n is not the total number of spins. It is just the nth spin. But there are spins over here. The system is something like this. This is the end point is somewhere thermodynamic limit. So this is 0 and that is n. So a chain of length L, you have the left hand side. And I'm focusing on two spins which are separated by n lattice spacing. If one should have, I mean, it is small n. When n hoche total number of spins, kintu what we are looking at is how does the spin S1, for example, here, when it correlate with this. So now, suppose I have to consider two different situations. One, there are two different things. 1 and n are parallel. And 2, 1 and n are anti-parallel. Due to that, there are just two possibilities. So when they are parallel, the S1, Sn is equal to 1. And when they are anti-parallel, then it is equal to -1. So question is, with parallel, how many configurations? With anti-parallel, how many configurations? And then divide out by the total configurations. That is the expectation. So how many configurations? So I have this spin up over here and this spin up over here. I can have no spin flip in between. So no spin flip anywhere. I cannot have one spin flip. I cannot, if this is up and this is up, then I cannot have a configuration which looks like this. So this is the boundary spin and this is the boundary spin. So I'm considering a case where the S1 is up and S1 is down, Sn is up. If S1 is up, Sn is up. If I look at the intermediate configurations of spin, no spin flip is allowed. You just have all of them in the same direction in between. One spin flip not allowed. Because, I mean, you have flipped once. If you have to have the boundary as up, you will have to flip again. This is fixed. This is fixed. This is fixed. Fixed. I can have no flip, but I can't have one flip. I can only have two flips. So I can have two flips, four flips, all the even flips. All right. So all the even flips, every time I flip in this chain, I have here e to the power beta j s1 s2 plus s2 s3 all the way up to sn minus 1 sn. No flip, let's call it 0, 1. 2 flips, then it has to be 4. So 2 flips is 4. So the energies that you are picking up, if it's an even number of flip, then it is 1, then it is e to the power 4 beta j, then it is 8 beta j, and so on. Right? So now comes the question of the up and down. So if it is up and down, so then it is minimum is 1 flip. So up and down, S1 up, so I have, these are my S1 and Sn configurations. So I can have 1 flip, or I can have 3 flips. So it is 1 flip, 3 flips, and so on. Right? So if it is -1, S1, Sn, if that is -1, then this is e to the power, where did I write what? So all right, didn't write anything. Very good. So this are parallel, then my allowed energies are, this is the no flip, 2 flips, 4 flips, and so on. And over here it is 1 flip, 3 flip, 5 flips, and so on. All right. Now, yeah. Huh? কোনটায়? হ্যাঁ, অ্যান্টি প্যারালাল যখন মানে এটা আপ এটা ডাউন, আমি যদি মাঝখানে কোনো ফ্লিপ না করি তাহলে তো হবে না। সো একটা ফ্লিপ আমাকে করতে হবে। হ্যাঁ, সো একটা ফ্লিপ কোনো জায়গায় হতেই হবে। সো তারপরে যদি আবার করতে হয় তাহলে কিন্তু 3টে করতে হবে। সো একটা চলছে যখন দুটো এন্ড পয়েন্ট যখন আপ আছে তখন 0 2 4 6, যখন এন্ড পয়েন্টটা উল্টে আছে তখন ইট ইজ 1 3 5। And so with the configuration, with this particular case, the energies are 1 e to the power 4 beta j, e to the power 8 beta j, and so on. এখানে হচ্ছে e to the power 2 beta j, e to the power 6 beta j, and so on. So these are the energies allowed. Now comes the combinatorial factors. So what is the combinatorial factor associated? N flips. So question of n flips, there are, let's say, over, that is why I was using capital N, so that I can use for flip small n. But anyway, if there, let's say m flips. So I have m flips. M flips can be done in m flips in NCM ways. That's how you can do. So therefore, that is the weight factor. And therefore, I have that it is on top, it is 1 plus, then it is 2, that was 2 flips. So it is NC2 e to the power 4 beta j plus nc4 e to the power 8 beta j, and so on. And then when it is minus, then I have nc1 2 beta j, nc1 2 beta j plus nc3 e to the power 6 beta j, and so on, divided by just all of them with a plus sign. Because the S0, S or S1, Sn, for all these S1, Sn is plus 1. This is the expectation value I'm calculating. For all these things, this one is plus 1 and this one is minus 1. So that's the so what you are looking at over, and then you have the denominator when it is just all plus, all just counting all configurations. But now what do you have in the numerator? 1 minus nc1 2 beta j, and this, that is the power series for sine hyperbolic 2 beta j. So what you are going picking up over here is sine hyperbolic 2 beta j, and then there is in the denominator it is cos hyperbolic 2 beta j, that raised to the power n, and this is the, so it is tan hyperbolic 2 beta j. So that's the correlation at and now the question is, what happens to this as now it is sine hyperbolic, cos hyperbolic, as beta tends to infinity, sine it is sine hyperbolic and tan hyperbolic are both the same. So therefore this correlation goes to 1 as beta tends to infinity, which is at t goes to 0. So the system does become correlated at this. At higher temperatures, this is going to beta goes to 0, tan hyperbolic goes to 0, and you lose the correlation. So you have the right features at t going to that you have. So the last bit, what is the correlation length? So what is the correlation length? That I have a very large beta. I have to do very large beta, t going to 0. So it is sine hyperbolic 2 beta j divided by cos hyperbolic 2 beta j, which is e to the power 2 beta j minus e to the power minus 2 beta j, e to the power 2 beta j plus e to the power minus 2 beta j, which is 1 minus e to the power minus 4 beta j, 1 plus e to the power minus 4 beta j. This is small, beta is large, so these are small. So this is very nearly 1 minus e to the power minus 4 beta j. So that's the correlation function, that it is 1 minus 2 e to the power minus 4 beta j, beta becoming t going to 0, this vanishes and it becomes 1. Now what is the correlation length expected to be? So where is my n? There was the n over here. I mean, sorry. Huh. So it is 1 minus n, the n, I mean, that is, you raise this, this is so small that you only keep the first in the binomial term in the binomial. So it is 1 minus 2n e to the power minus 4 beta j. That's the, and the correlation function, the length would be the, you want the correlation to die down as e to the power minus, so the correlation function dies off, so as e to the power minus n over xi, so that is the correlation length. And so for very large xi, this is 1 over 1 minus n over xi, and then you compare and find that xi is equal to e to the power 4 beta j over 2. So the correlation length blows up. Just a bit, this force sound doesn't look very good. What's going on? I mean, it is e to the power, but 4 is what happened? I did the correlation, it is 2 beta j. These are 2 beta j, 4 beta j, 6 beta j, that's how it goes. Four and beta. What in the world is going on? That force sounds a bit too big. But anyway, I mean, that's something that you can this seems a little too big to me. I would have been happier with a 1 or a 2, but something somewhere. I should have started with, I had a 1. What happened to the 1 in the partition function? That was the cos. Something a bit worried about. Anyway, they will fix it, have a look. But the thing is done. I mean, the point is that this is exactly how it goes. I think that there is some error somewhere over here. It should have been, I mean, this 4 beta looks a little too strong. Somewhere I have overdone the energy factor somewhere. But the susceptibility diverges exponentially. The correlation length diverges exponentially. So that part works out, but the susceptibility was e to the power 2 beta j, and therefore I would have expected the correlation length should have been weaker or equal. So that is why I'm a bit troubled by the 4, maybe. Anyway, but the point is exponential divergence of the correlation length as you come over here, and that is everything that you can do with the 1D Ising model with next nearest neighbor interaction. We did all the thermodynamic quantities. We have done the correlation length also. just have a look at what the whether this there is some error, I'm sure, in the 4 over here. Should have been little better done. Anyway, so that's that. But next time we will do see what is a different way of getting at this answer, so that this is not, this transfer matrix is virtually impossible to in this form take it up to the 2-dimensional case. So the 2-dimensional problem is far more difficult, and I'll explain why, and we'll see how it gets. But then I will do the calculation for the correlation length in the 1D in a from a very different perspective, a perspective which you will find would also work, not exactly but approximately, for the d equal to 2. So that is why it is worth the next class, doing the correlation length in a slightly different manner is worthwhile, because it lays the groundwork for something else. So all right, so that's it. So next time